Hello, friends. Dolphin here from Com Advantage. But if you don't know who I am, I don't know, maybe that's important. So we're going to talk about doing some volume with a can today. And I will say that this question, I was like, oh my goodness, we have to go back to like so many high school-esque formulas in order to be able to do it. And so like it's a company, they make tin cans, they have a volume of 200 cubic centimeters. The metal used to manufacture the cans costs a cent per square centimeter on the sides and 2 cents for the thicker top and bottom. What should the dimensions of the cans be to minimize the cost of metal in their production? Okay. And so we're dealing with a circle. We're dealing with the volume of a cylinder. And we're actually, when we look at the side, you can even see on this can, there's a line there because this was one big rectangle that got curved, which means that the length of the rectangle is actually the circumference. Oh, that I had to pull that word out from a long time ago of the circle here. And I know that like in business classes, this is not, we're not normally dealing with cans and volumes like this. This is not the type of question that usually shows up on the exam because it requires you to have memorized these formulas. Okay. So before we actually get into solving this question, let's just recap on those key formulas that we actually need. So for a cylinder, the volume of a cylinder is going to be pi r squared times height. Okay, so h is the height of the can, and r is the radius of the circle. Okay? And to remind you, the radius is from the center point to the edge. So diameter is the full width across, radius is half of diameter there. Okay. The area of a circle is just that pi r squared. The volume of the cylinder is literally us taking this area of the circle and just multiplying it by the height to get the volume. Okay. And then the other thing that we needed was the circumference. If I spelled this wrong, please do not yell at me. Um, this is 2 pi r, okay? And so again, when we think about a can, right, it's that circle, straight down type thing. And so the side of the can is actually just going to be that metal where we have the height, but that the length is going to be the circumference. Okay. Our top of our, let's see, can here is a circle. So that radius there is going to be there. And so the area here is that pi r squared. Okay. Just a preamble. Because what we want to recognize with any question like this is just constrained optimization. Okay. And with constrained optimization, there's the thing we're trying to maximize or minimize, and then there's the constraint. So in this problem for constrained optimization, the thing that we are trying to, in this case, minimize is the cost of the metal in the production. So our goal is to minimize that cost of the metal, and our constraint, which sometimes you'll see with the little ST meaning subject to, is that the volume of the can, volume, yes, very self-conscious today about my spelling, has to be 200 cubic centimeters. Okay. And so we have to have formulas for each of these things in order to actually go through and do the math part of this problem. Because in constraint optimization, step one is to actually get our equations. Step two is to solve the constraint, that formula, and sub into the main formula. And I know somebody on YouTube finds me, and I'm not using real mathy terms here because it was math for business students, and like we're just trying to get through things, okay? And then once we've done that, we take the derivative of that main function, and we're going to set the derivative equal to 0 and solve for our critical point. Okay. There is an implied endpoint in any of these things that the values cannot be 0. We're always going to get for volume related things an answer of 0 because that's our minimum volume, is that it doesn't actually exist. Okay. So that's what we're trying to do. But in order to do this, we need all of our fancy formulas. And that's the tricky part that's going on here, in all honesty. Okay. Now, if this was on an exam question, we'd always actually want to start by defining our variables. So our solution is that we would say, well, let H represent the height of the can in centimeters. Let R represent the radius of the can in centimeters. That looks like corn. Okay. And our objective function here, right, the thing that we're trying to minimize is that cost of the metal. Okay. So our goal here is to minimize that cost, where it told us that it was going to be 2 cents for the top and the bottom of our can, right? So it's 2 cents times the area of the top plus 2 cents times the area of the bottom plus it's 1 cent for the area of the side. And so that area of the top and the bottom is actually the same, and that is going to be the area of our circle, okay? So we're going to have 0.02 times the area of our circle, which is pi r squared. And you can write this out. I'm going to use brackets for my multiplication just so we don't think that that's an x variable somewhere. You can write it out again. This is for the bottom times pi r squared. And then for our rectangle, right? Again, the height is just the height of our can, no problem. But the length of this rectangle is the circumference of the circle. So it's going to be that 1 cent times that height. And then for our length is going to be the circumference of our circle there. Okay. And so our circumference is 2 pi r. And if you want to make a note of that like separately, right? That area of the side, length times height, the length is the circumference, and our height is our, well, height Okay. And of course, we'd like to simplify this as much as possible. So we're going to have 0.04 times pi r squared plus 0.01 times 2 is going to give us 0.02 pi r times h there, okay? And so this is the equation that we're going to try to minimize, but we also had that constraint that the volume had to equal 200 centimeters cubed. And our formula for volume, as we said, is going to be our pi r squared times height. And so we've set up our equations, but now we want to solve the constraint for a variable. It is up to you whether you solve for the r or the h. Because the h doesn't have a squared term, it's actually a little bit easier. Just going to divide both sides by pi r squared. And so I end up with h being equal to 200 divided by pi r squared. And so then our next step here is to plug the constraint into our equation. So if we know that our cost equation is that 0.04 times pi r, oops, terrible pi squared plus, oh, what did we simplify this down? 0.02 pi r h. Oh, we can't see that. We're just going to replace the h with what we figured out it equals. So then we're only going to have r's. Because remember, pi isn't a variable. Pi is 3.14, goes on for forever. It's a number in your calculator. Pi is a very magical number, okay? And if you want to know more about that magic, you can talk to my very nerdy husband. Okay. So we're going to have that 0.04 pi r squared plus 0.02 pi r 200 over pi r squared. Before I take the derivative, I always like to simplify if possible. Oh my goodness, I am already tired of this problem. 0.02 times 200 is going to be 4. Nope, nope. Why did I think that? Yes, it's going to be 4. Um, right? Because all of this is related by multiplication. So we can multiply the 0.02 with that 200. The pi is divided by pi, so that's going to cancel out. I have an r on top and an r squared on the bottom. So remember, that's like having r over r. So those cancel, and I'm just left with an r in the denominator. So this ends up just being 4 divided by r. Okay. When we're going to take a derivative, most people do a little bit better with um, things written with the negative exponents instead of just being in the denominator there. It doesn't matter, it's totally up to you. But now we're going to take the derivative. And so the derivative of our cost with respect to the radius, because remember, pi is just a number. So this squared term is going to come down. So we're going to have our 0.08 pi r. And then I'm going to have negative 4 r to the negative 2, right? So that negative 1 is coming down, multiplying by the 4, and then we're subtracting 1 from that exponent. We're going to set this equal to 0. 0.0 is equal to the 0.08. Now, for me, when I go to rearrange equations, it's actually better for me to have those um, negative exponents moving the variables to the denominator where they don't have the negative exponents, just for the sake of rearranging, because I'm a visual rearranger. You do whatever is best for you, okay? So I'm going to move this over. I'm going to have 4r squared is going to be positive because I moved it over with an r. I want to get all the r's on the same side, so I'm going to multiply both sides by r squared here so that these ones cancel out, and I'm left with 4 is equal to 0.08 pi r cubed. I want, again, our term just all by itself, so I'm going to divide by that 0.08 pi, and I'm left with r cubed. Now, if I put 4 divided by 0.08 times pi, oh, like, where is pi on my calculator? So if you have the Casio 991, which most of you should have, the pi is in the secondary function over top of the um, 10x button here. Okay, so you would hit shift and hit that button, and it will literally show you that pi symbol. And the point that I wanted to get at is that if I put that in my calculator, I get a nice long crazy decimal. And so I could use that decimal. I could write down 15.915494431. And that's fine. But also recognize with really messy fractions like this, sometimes you just want to wait till the very end to put the whole thing into your calculator, but it's about playing to your strengths. Now, to get rid of the cubed, we take the cube root. I just want you to recognize, because like it happens to be a cube, maybe it was like a 3.84 or something weird. We're always just raising both sides to 1 over whatever that exponent is to get rid of it, right? Because if I have x to the a times 1 to the a, or to the exponent 1 to the a, this, we end up multiplying our exponents, right? And when we multiply a times 1 over a, we get x a over a, which is just x to the 1, which is just x, okay? So we always want to keep that in mind because sometimes with our really weird exponents, we get stuck and we just want to make sure that we're okay there. So when I do this, I get that the radius is 2.515. A radius is going to be in centimeters because the whole thing was in centimeters there, okay? And now that I have that radius, I want to go back and find the height. I'd also probably like to actually check that this gives me a minimum. So to check for our minimum, we're going to do our second derivative test. Okay, and so our first derivative there was that 0.08 pi r. Yep. And then minus 4 to the negative 2. And so if we take our derivative again, we're going to have 0.08 pi plus, because this negative 2 is going to come down and multiply with the negative 4. So negative 4 times negative 2 is going to give us 8 r to the negative 3. And so if we plug in that point of 2.515, everything in here is positive. We get a positive number back, right? Remember, positive smiley face, and therefore we have a minimum, right? This is a minimum. And then it's really just about like, well, what else did the question ask you? Okay. So we know that that radius is 2.515 centimeters. To get our height, we go back to that constraint, which was 200 divided by pi r squared, and we're just going to plug in. Right. So height, we get 10.068. Um, this is a good, I'm glad we hit this. Because if this is our answer and we wanted to round this to two decimal places, oftentimes people will say, well, 0.6, the 8 turns the 4 into a 5, and so that means that I've got 10.07. This actually rounds to 10.06. And it's better to think about it as like 48 is less than 50. So it's going to round down. Now that this is quite sensitive, quite sensitive to what you put in there, in terms of rounding for the radius. So just whenever you're doing this, always watch the instructions that you're given for your rounding. And then we can find out the total cost if we want, right? We can go back to our original cost function, which was that 0.04 pi r squared plus 0.02 pi r h, and just fill in our values. So if this had told us to round to two decimal places, I just realized that I was inconsistent with my rounding of each. Round to two decimals. Then we're going to use for our radius 2.52. And so if we plug that in instead, we are going to get 10.0249, which is still going to round down, not up. Okay. And I just want to, just so that I was using two decimal places in each of these. Typically, if I'm doing something that isn't for like a weird commerce exam, I'm going to actually carry uh, those extra decimals throughout and then only round at the very final answer. But I do believe that in your um, like weird digital homework, it assumes that once you've rounded your radius, you'd also use that number in your height, and then you'd round your height and you put that into your cost function. I could be wrong. I'm really not in it for the rounding for specific learning platforms, but more, hey, do you actually understand what we're doing here and how to set these questions? Okay. And so our cost here, we get $1.30. And there you go.